1368. Minimum cost to make at least one valid path in a grid. Imagine you are given a grid, where each cell has a sign pointing in a specific direction. Your goal is to find a path from the top left corner, 0, 0, to the bottom right corner, M1, N1, while following the signs. If needed, you can modify a sign, but each modification comes with a cost. What's the minimum cost required to ensure at least one valid path exists? Question: how can we find the minimum cost to modify the grid and create a valid path? Problem explanation. Rules. Each cell has a sign. 1. Move right. 2. Move left. 3. Move down. 4. Move up. Modifying a sign incurs a cost of 1. Challenge. Some signs may lead outside the grid. Find the valid path from 0, 0, to M1, N1, with the least modifications. Question: what are the rules and constraints of the grid problem? Brute force approach. Explore all possible paths starting from 0, 0. Keep track of the total cost for each path. Check if the path reaches M1, N1 limitations. Inefficient for large grids due to exponential complexity. Question: how does the brute force method solve this problem, and why is it impractical for larger grids? Optimized approach using Dijkstra's algorithm. Treat the grid as a weighted graph. Use a priority queue to prioritize cells with the least cost. At each step, update the cost of visiting neighboring cells based on whether modification is needed. Stop when reaching M1, N1. Benefits. Efficient for larger grids. Guarantees the minimum cost path. Question: how can Dijkstra's algorithm optimize the solution for this grid problem? Comparison: brute force. Tries all paths. Inefficient for large grids. Dijkstra's algorithm. Focuses on cells with minimum cost. Scales well with grid size. Outcome: both find valid paths, but the optimized approach is faster. Question: how do the brute force and optimized approaches compare in efficiency and scalability? Example walkthrough sample grid. 1 right pointing arrow, 1 right pointing arrow, 1 down pointing arrow, down pointing arrow, down pointing arrow, 3 3 3 down pointing arrow, down pointing arrow, down pointing arrow, 3 3 3. Steps. Start at 0 0. Follow the signs while modifying cells if needed. Use Dijkstra's algorithm to find the path with minimal cost. Result: path 0 0 right pointing arrow, 0 1 right pointing arrow, 0 2 right pointing arrow, 1 2 right pointing arrow, 2 2. Total cost 1. Question: how does the algorithm solve a 3x3 grid problem step by step? By combining problem-solving strategies with optimized algorithms, you can efficiently solve grid-based challenges. Try implementing this solution and test it with your own grid scenarios. Are you ready to apply this approach to more challenging grid problems? Thank you.